Hey, welcome back everyone. So hopefully you found the quiz okay. So let's continue with our review of linear algebra. So in the last lecture we covered Taylor expansion for functions of multiple variables. So I think most of you probably are familiar with Taylor expansion for one variable, but in this class we're going to be mostly using multiple variables. We also talked about quadratic forms and visualized some examples. And then lastly, at the end, we kind of did a review of the previous concepts. So today we're going to begin with quadratic forms again. So again, this is the quadratic form, x transpose ax, the variable is x and a is given. We looked at the different appearances. So for example, when a is positive definite, x transpose ax would look like an upward opening bowl. And if a is negative definite, then the quadratic form looks like it kind of opens downwards. When a is positive semi-definite, overall it opens upwards, but there could be some directions that are flat. And then similarly for negative semi-definite, it opens down in general, but in some directions it could be flat. And for indefinite, in some directions it opens up, and in other directions it opens down. And all of this, of course, extends to when you have more than two variables in the quadratic form. So in this case, we're assuming that the vector x only has two components. That's why we can plot it using the third dimension as the value of the quadratic form. In general, x could have many components. In machine learning or computer vision, it could be thousands, for example. Okay, so this is basically visualization of the quadratic form, and so far we've been assuming that a is symmetric, right? But in general, when you get some a here, it could be non-symmetric. Mostly we've been assuming that a is symmetric because quadratic forms will show up whenever we have the second order Taylor approximation of a multivariable function. So we already talked about how the Hessian is always going to be symmetric. So mostly a will be symmetric. However, sometimes a could be non-symmetric in general. If we kind of think outside of Taylor expansions, then a could be non-symmetric. So what would these pictures look like? So what do we know about symmetric or non-symmetric A? Well, for non-symmetric A, the eigenvectors are not necessarily orthogonal as we have seen. They sometimes would even be pointing in the same direction. So what would happen? Well, let's do a little bit of math to see, right? So let me do this a bit more slowly. Okay, so I guess basically the short answer is that no, even when A is non-symmetric, nothing weird would happen. So the way we can see this, again, some of the math could be a little bit cryptic, but in math, we can do whatever we want as long as it's correct. So how about I do it some other way, right? Maybe just to be a bit clear. So we know that A is equal to A over 2 plus A over 2. And in math, we're allowed to do something as long as it's correct. So first splitting A into A over 2 plus A over 2, that's correct. We'll do it. And then next, we can always add A transpose over 2 and then subtract A transpose over 2. That's correct, so we can do it. And of course, we can do many things, but doing it in this particular way will allow us to simplify things a little bit and make a good argument. Okay, so let's write A this way, and then the quadratic form will become, well, everything. So x transpose x, and then instead of A, we're going to write everything in here. right? Everything up here. Okay, so that's the quadratic form. And it turns out that when you have a matrix in the middle for quadratic forms, you can actually separate them out into two different quadratic forms. The first one involving just the first term of the sum inside the brackets, and the second term involving the second term. Yeah. Okay, so that's good. So we're gonna focus actually more on the second term here and see what exactly it is. This one. Okay, so we're gonna work a little bit more over here. So x transpose A minus A transpose over 2 x equals 2. So let's expand this out a little bit. So the 1/2 comes in front, and then we're gonna split this matrix just as we did before. So the first part of this matrix is actually gonna be 1/2 x transpose A x, and then the second part is gonna be minus 1/2 x transpose A transpose x. Okay. So now what do we, so for the next step, actually there are two ways we can do it. The slide shows one way. I'm gonna, just for some extra, just to show you a little bit more, I'm gonna do it the other way. So here we're gonna look at x transpose A transpose x. Right, so let's continue over here. So first of all, the first thing we notice is that x transpose A transpose x is a scalar. Because this is a vector. And then when we take x transpose times a vector of the same dimensions, we get a scalar. So one property of scalars is that when you take their transpose, nothing changes. Okay, so we can take transpose without changing it. So x transpose A transpose x, all transpose would equal to x. So when we take the transpose, we do it backwards for the individual elements inside the big bracket. So the first one is going to be x transpose, and then next we have A transpose transpose, that gives us A. And lastly, we have x transpose transpose, that gives us back x. Okay, so it turns out that this part, even though we have an A transpose in the middle instead of an A, right? So kind of comparing the A and the A transpose, even though initially they kind of looked different, it turns out that they're the same thing, because of the fact that we can take the transpose of the scalar and get the same thing. So therefore, this whole thing, so this x transpose A minus A transpose over 2x, right, continuing from up here, that whole thing just equals to 0. So this whole thing becomes 0. That's supposed to be a 0. And then what we're left with is just simply x transpose A plus A transpose over 2x. Okay, so that's kind of why we wrote A out this way initially, because we kind of, I knew that the second term would become 0, right? So now we're left with one term. And when we look at this one term, the important observation here is that this part, A plus A transpose over 2, is symmetric, right? Hopefully we can try to see this by inspection. But if we cannot figure this out by inspection, one easy way of figuring it out would be to simply take the transpose of this thing and see what we get, right? So we get A transpose. So when we're adding things and then taking the transpose, we can simply take the transpose and then add. So A transpose plus A transpose transpose, that gives us back A. And of course, over 2 doesn't really change, right? So you can see that this is actually just equal to A plus A transpose over 2 because the order of addition doesn't matter. Okay, so it turns out, so what is the final conclusion here, right? The final conclusion is really that whenever we have a quadratic form involving A, where A may be non-symmetric, it's actually, this quadratic form is actually exactly equal to another quadratic form where the matrix is symmetric, right? Which we have just shown it here. So that means that regardless of whether A is symmetric or not, the quadratic form won't really look very strange. Like weird things won't happen just because eigenvectors are not orthogonal. Because in order to figure out what this looks like, we can always first compute A plus A transpose over 2 and then figure out what this quadratic form looks like. Right? And that's going to look like one of the pictures that we showed in the last few slides. Okay, so that was the math here. In the slides, we're doing something a little bit different, but I think in spirit it's basically the same. You can kind of go through this. Basically, we're just writing this. We're actually combining the two transposes into one, and then noticing that we just simply have an inner product here. And then when we compare the two terms, we see that we just have the inner products happening in different orders. But we know that the order of the arguments of the inner products doesn't matter, right? So this is another way to show that the second part here becomes 0. Okay, so final conclusion, X transpose AX equals to X transpose, and then inside A plus A transpose over 2, finally times X. And then, of course, this thing in the middle here is symmetric. Okay, another property that would be pretty interesting is A transpose A is always going to be positive semi-definite. So how do we show this? So this is actually a pretty typical linear algebra question, and that is pretty relevant to machine learning. So we're gonna do this a bit slowly again, right? Hopefully, when you see some of these tricks a bit more often, you'll get a good idea of what to do in general when it comes to proving something. Okay, so we want to show A transpose A is positive semi-definite. So remember, we kind of have two options because we have seen two different definitions of positive semi-definiteness, right? So option 1 could be to look at X transpose A transpose A X and then see whether, and then check if this is greater than 0, right? Maybe not check, but confirm, I guess, because in this proof, we kind of said that, well, we know what the result we want is, right? So we're just going to confirm that this whole thing is greater than or equal to 0. Second option is look at eigenvalues of A transpose A. Okay, so this is kind of like a general strategy whenever we do any proof in math, right? We kind of start with what we know. How do we show that something is positive semi-definite? Well, we go back to what it means to be positive semi-definite. We have learned two definitions, so the way we do the proof must be using one of the definitions. So the second option, looking at the eigenvalues of A transpose A, well, this one seems a little hard because we have no idea what A is. A could be anything, literally. And computing eigenvalues is somewhat of a process, right? So without knowing anything about A, it doesn't seem like option number 2 is very promising. So we're going to go with option number 1. Okay, so for option number 1, we're going to do a bit of calculation. First by writing out the starting point. Okay, so what does this equal? So now we're going to try to manipulate this expression bit by bit until we get something that looks like it's greater than or equal to 0. So the first thing we're going to do is to get rid of the brackets, because in matrix multiplication, it doesn't matter which order. It doesn't, like, as long as you keep everything the same order, it doesn't matter which multiplication you do first, whether you do the left, whether you do these two, x transpose a transpose first, or the last two first, it doesn't matter. So we can remove the bracket. Okay, seems like a trivial thing to do, but we are making some progress. Okay, so next we notice that, you can kind of see the symmetry here, right? So we have AX on the right here, and then we have X transpose A transpose. So what we're going to do is we're going to combine the two transposes into a single transpose, just AX transpose. And then basically we can see that we have AX, all that transpose, times AX. So this is basically some vector transpose and then times some other vector. What this means is that we have actually an inner product of something with itself. And we know that based on the definition of, based on the property of inner products, this is always greater than or equal to 0. Okay, so this shows that A transpose A is always positive semi-definite. Okay, so going back on the slide again, so remember we took option number 1, which is to look at the quadratic form and show that this is greater than or equal to 0. So we did some kind of rearranging of the brackets, combining the transpose here, using this property, and then noticing that this is exactly just an inner product of AX with itself. Okay. So now, because the two arguments of the inner product are the same, this is always going to be greater than or equal to 0, right? So on the slides, I'm doing even one more step. When you do the inner product of a vector with itself, you actually get the squared 2 norm of that vector. And we know that 2 norms are always greater than or equal to 0. So the 2 norm is also called the Euclidean norm. Okay, so that shows, okay, so again, we didn't make any assumptions about what A is, and we also did not make any assumptions about what X is. Regardless of the A or the X, this statement is always true. Okay, so that shows that for any matrix A transpose A is positive semi-definite. Okay, next we're going to talk about the very important concepts of convexity and concavity. So let me give you the mathematical definition and then explain the picture, and maybe I'll draw another picture just to be clear. Okay, so a convex function is defined by, kind of colloquially, by this property: a line segment joining any 2 points on the surface lies on or above the surface. So that means that if I, maybe I can annotate a little bit. So if I pick any 2 points on this surface, let's say this point, and then let's say any other point, right? Doesn't matter. And I draw a straight line between them, then the line is always equal to or above the actual surface. So the surface would be something like this, and we can kind of see that the surface is actually below the line. The line is above the surface. So that's the kind of the picture here. Mathematically, we write this as alpha. So for any alpha between 0 and 1 inclusive, we have that alpha f of x plus 1 minus alpha f of y is greater than or equal to f of alpha x plus 1 minus alpha y. Okay, so hopefully you remember that whenever we do a linear combination of things, in this case on the left hand side we have f of x and f of y, and then on the right hand side inside the argument of f, we're actually taking the linear combination of x and y. Right? Whenever we have linear combinations where the coefficients add up to 1, that's actually called a convex combination. So another way of saying this is that the convex combination of the function value is always greater than or equal to the function evaluated at the corresponding convex combination of the inputs. Okay, this is kind of a mouthful. Let me try to draw another picture to make this a bit more clear. Kind of how relating the math to the diagram here. Okay, I guess we have a bit of room on the right side here. Okay. So we didn't do option number 2 in the previous example. Okay, so let me just write down. So I'm going to do a scalar example where x is just a scalar variable. So for a convex function, it always satisfies this property. Alpha f of x plus alpha plus 1 minus alpha f of y must be greater than or equal to f of, and then you apply the convex combination inside, right? Alpha x plus 1 minus alpha y. Okay, left hand side is always greater than the right hand side for all alpha between 0 and 1. And then for all x, no restrictions on x and no restrictions on y. So that's really important. Some function may have this property for some x and some y, but maybe not for all x and y, right? So for a function to be convex, we need this property to hold true for all x, y. Okay. So let me just draw a convex function. So this is f. And so now for all x, y means that we can pick some arbitrary x and y. So arbitrarily, yeah, I mean, we can pick anything, right? Any of these could be x or y. So let's, for the sake of the diagram, I guess I'll pick this one to be x and this one to be y. And then anything, so we're going to go a bit slowly, right? So x is here on the left, y is here on the right. When we take alpha x plus 1 minus alpha y, that will be some point in the middle here. So for example, when alpha is 1/2, we would have 1/2 x plus 1/2 y. That would actually be the exact middle. As alpha, when alpha is 0, we have 0 plus y. So that would be y, right? So when alpha is 0, we're all the way on the side of y. And when alpha is 1, we're all the way on the side of x. And then for some other alpha, we're just going to be somewhere alpha of the way from y to x. So basically, alpha x plus 1 minus alpha y will be some arbitrary point between x and y, inclusive. So basically, we have taken care of quite a few variables inside here, right? So we have understood what x is, what y is, but also what this entire thing that we're plugging in to f is on the right-hand side. So now let's work a little bit more on the things that we haven't taken a look at. So we have actually f of x. So what is f of x? So f of x is simply the value of this function at x. So this is f of x. And then f of y will be the value of the function f at y here. Okay, so let's see if I can draw a horizontal line. Okay, not quite, but hopefully you get the idea, right? So this would be f of y. Okay, and so we have f of x, f of y. The last thing we need is f of alpha x plus 1 minus alpha y. So we need that thing, right? So that is actually basically this point here. We basically plug in alpha x plus 1 minus alpha y, and that gives us f of alpha x plus 1 minus alpha y. Okay. I think we're almost done here. The last thing we need is a kind of looking at the entire left-hand side and figuring out what that means. So remember when I remember just a while ago, I said that we have x here and y here. When we take alpha x, when we take a convex combination of x and y, depending on alpha, we're basically going to be somewhere in between x and y. So the same argument is true for f of x and f of y. So we have f of x here, f of y here. Whenever we take a convex combination, alpha f of x plus 1 minus alpha f of y, we're just going to get a result that is somewhere in between. Whenever alpha is 0, we get f of y exactly over here. Whenever alpha is 1, then the second term is gone, and then the only thing we're left with is f of x. So we can actually represent the left-hand side of this inequality as a line joining these 2 points. In the line joining these 2 points, the value of that line at the location alpha x plus 1 minus alpha y will actually be exactly alpha f of x plus 1 minus alpha f of y. Okay, so for this one, maybe take a closer look after the lecture if it's still unclear, right? And if that's still unclear, please ask me on courses forum. Okay, so now we have labeled everything on the diagram that we see in the equation, and we can now visually just check what's really happening, right? What is really happening is that for a convex function, I can pick any x, any y, and the line that I draw that connects these 2 points, which is the left-hand side, will be always above, greater than or equal to, the function evaluated at the same point, right here. Okay, so roughly speaking, this will always happen whenever you have a function that opens up, right? If you have a function that opens up, like a bowl-shaped function that opens up, you can always draw a line between any 2 points on the function, and then that line will lie above the function. Of course, this applies to multivariable functions as well. So hence, so kind of coming back to this example, right? I can pick any x, any point on the surface, any 2 points on the surface, and then if I draw a line between them, the line is above the function. So that's exactly what this math is saying. Whenever this happens, the function is called a convex function. So we actually have 2 definitions of this. So another definition is that the Hessian of the function is positive semi-definite everywhere. Okay, so in this particular function, this function is actually f of x equals to x transpose ax, where a is equal to 1, 0, 0, 0. So this A matrix is actually positive semi-definite. So this is actually the Hessian of the function as well. So in this case, it just equals to x1. So x1, I guess, is going to be just this component, right, this direction. So no matter what x1 you plug in, sorry, this is actually x1 squared. No matter what x1 you plug in, x1 squared will always be non-negative. So therefore, the entire function will always be non-negative as well, right? So equivalently, the Hessian of the function is positive semi-definite. So this is a convex function. So very closely related to strictly convex function is strictly convex function. So the definition is exactly the same, except that we have a strict inequality here. Whenever alpha is strictly between 0 and 1, alpha f of x plus 1 minus alpha f of y is strictly greater than f of alpha x plus 1 minus alpha y. Okay, so in this case, we have to be a bit careful with the Hessian. So we can use the Hessian to tell us if the function is positive definite. So if the Hessian is positive definite everywhere, then the function is strictly convex, but not necessarily the other way around. Okay, so for this one, for the semi-definite case, the Hessian being positive semi-definite is actually equivalent to the function being convex, right? So it goes both ways. If the function is convex, then the Hessian will be positive semi-definite, and if the Hessian is positive semi-definite, then the function is convex, so equivalent. For strict convexity, the function being convex would imply, the function being convex may not imply that the Hessian is positive definite. But if the Hessian is positive definite, that implies that the function is strictly convex. You can kind of see that this is more of a real bowl shape, right? So when you draw a line connecting 2 points on the surface of the function, right? You can see that the line is strictly above this the surface. Whereas on the previous slide, I could have drawn this line. Let's say I pick these 2 points, and I draw a line connecting these 2 points. You can kind of see that the line is actually exactly on the surface, so that still satisfies greater than or equal to, but not strictly equal to, right? So if you can draw a line that is exactly on the surface but not strictly greater than, you may have a positive semi-definite Hessian, or equivalently a convex function, not necessarily strictly convex. Okay, so hopefully that made some sense. Okay, let's continue with some very related definitions. So once you get convexity, then concavity would be basically the same thing, right? Except that we now have the function, opening downwards. The inequality has switched, right? And then the comments about the Hessian is also going in the other direction. So the Hessian, so for concave functions, the Hessian of the function will be negative semi-definite, and it's actually equivalent, right? If I just go back to convince you that the sign has flipped. So line above surface, greater than sign here. And here, if I draw a line, it's going to be below the surface, less than or equal to sign here, and negative semi-definite. Okay, maybe you already expected this, but lastly, we have to cover strictly convex functions. So a line segment between any 2 points is going to be strictly below the surface. So strictly below, strictly less than here, and also the Hessian is negative definite. Okay, again, be careful with the Hessian here. If the Hessian is negative definite everywhere, so no matter what x you plug in, that means that the function is actually concave, strictly concave. Of course, that also means that the function is concave, but not the other way around. So if the function is strictly concave, it may actually not have a Hessian that is negative definite. I believe we'll be looking at some example coming up. Okay, so now a more general concept is called Jensen's inequality. So the definition of convex functions basically looks at 2 points and 2 function values. So 2 points x, y. Okay, I need a bracket over here. And then 2 function values, f of x and f of y. So Jensen's inequality generalizes this to any number of points. So instead of having 2 terms, instead of having a convex combination of either 2 function values or 2 input vectors, we actually have n inputs and n vectors here. So n function values and then n input vectors here. So because we have a convex combination, all the alpha i's must be greater than or equal to 0, and the sum of them must be equal to 1. So hopefully you remember the general definition of convex combinations. Okay, so this is for convex functions, of course. It's actually pretty easy to see why this is the case. So let me try to draw another diagram. This one might be a little challenging, but I'll try. Okay. So basically I'll have to do things in 3D now, right? So I'll do 2 variables, but you can imagine more variables would work as well. So here we have x, the vector x equals to x1, x2, right? But in general, it can go up to xn. So a convex function basically looks something like this. We have a bowl-shaped function, as we have seen, right? So here's kind of my attempt at drawing a bowl-shaped function. So basically what Jensen's inequality is saying is that on the right-hand side, we're going to take a convex combination of the input vectors. So let's just have let's say let's just do 3 points, right? We have 3 input vectors. We're going to take the convex combination of them. Whenever we take the convex combination, the result will always be in the convex hull of all the points. So in this case, it will be everywhere inside the triangle. So this is going to be the set of input vectors that we're going to be looking at on the right-hand side. So the question is, what happens when we plug any of these points into F? So when we plug any of these points into F, well, let's say that the 3 points are something like this. Okay, sorry, not a good artist. So it could be these three points. So it's going to look like this, right? So the function is curved, so maybe it could be something like this. Okay, and then this kind of goes behind the function. So this is kind of the portion of the surface which is the result of evaluating all the input vectors inside the triangle. So now we're going to look at the left-hand side over here. So this is basically a convex combination of the function values. So using the same intuition we had, this is basically actually connecting these 3 points using a straight line. I think probably a different color would be helpful here. So let's do all the inputs in green, right? So all of these should be in green. So the input points are anywhere from inside the triangle. So that's the convex combination of the input vectors. The convex combination of the function values is going to be a plane that intersects, is going to be a plane formed by these 3 points. I know it's a bit hard to see here, but these 3, the plane is always going to be above the portion of the surface corresponding to the inputs, right? So maybe if I try again on some other, maybe I can try again here. So here we have the convex function. So if we evaluate the function at 3 points, we might get something. Yeah, let's do. Yeah, I guess definitely not a good artist. So let's try these 3 points. So maybe 1 point here, 1 point back there, and then maybe 1 point here. Right? So you can kind of see that the portion of the surface, which is the result of evaluating the triangle down there, would look something kind of like this. Okay, right, so it's going to be this portion. Okay, maybe I shouldn't keep track, right? It's going to be this portion over here, but the shaded portion is always going to be part of the surface. And then, yeah, actually, sorry, I think I gave up on this, but maybe I'll try to do the same thing on the slide. That might be a bit easier. So here's the convex function. If we take 3 points, maybe these 3 points, then when we evaluate the triangle beneath, right, maybe something like this. So that might be the triangle that we evaluate. Right, the result we get, we'll get is going to be something like maybe everywhere here. So shading this part, and then a little bit back here, right? But the point is that the shaded area is always going to be on the surface. But the convex combination of the 3 points themselves will actually be a plane that is formed by this triangle. So this plane, as you can see, is kind of sitting on top. It's kind of sitting on top of the bowl, right? Whereas the bowl's surface is below this plane. So this this kind of pictorially illustrates Jensen's inequality. Okay, so hopefully that made sense, even though I'm a terrible artist. Okay, so that's Jensen's inequality for convex functions. And for concave functions, the inequality goes the other way. So now we're going to look at why convexity is very important. First, I want to kind of go back to first year calculus and remember how you guys did. I think some of the questions you guys did are something like find all the critical points of a function and then classify them as local maximum, local minimum, and so on, right? So hopefully all of you have done that in first year calculus, and hopefully you remember. In machine learning, it's all about finding the point that minimizes the loss function, because that means that our model has the least amount of error given those parameters, right? So in machine learning, the x will be the parameters. So, and then we want to pick a parameter such that the loss is the lowest. So something like this point. Okay, so I guess formally what we want to do is, given a univariate function, so a function of one variable that is everywhere twice differentiable, how can we find points where f is minimized or maximized? So the first step, as you remember from first year calculus, is first find all the critical points. So these are all the points where f prime of x is 0. So the derivative of f evaluates to 0 at these points. So that's going to be this point here. These 2 points could be this point, these 2 points. So for all the critical points that's where f prime of x is 0, the points could be global minimum, local minimum, which is this case, could be local maximum, these 2 cases. It could be a saddle point. Saddle point means that in one direction it goes up, in some other direction it goes down. It can also be a global maximum as well. Okay, so now after we get the critical points, the next step is to use the second derivative to figure out how to classify each of the critical points. And hopefully you remember that what you do is you take the second derivative and you evaluate the second derivative at the critical points. And if the result is that the second derivative at the critical point is positive, then we must have a local or a global minimum because it opens up. If the second derivative at the critical point is negative, then we must have a local or global maximum, something like this. And if the second derivative of 0, then the result is inconclusive. It could be a local or a global minimum, a local or a global maximum, or a saddle point. So the same thing is going to be true for multivariate functions. So now we basically generalize what we have done in first year calculus to multivariables. So now all the critical points are going to be the points. So now each point is a vector x. So all the points x such that the gradient of f is equal to the 0 vector. So if we find all of these points, then these points could be a local minimum, like in this case, the bottom, a local maximum, the top. So basically the gradient being 0 means that locally the function is flat, right? Horizontal. The third case is that it could be a saddle point. So here at the middle here, the function is actually locally flat, locally horizontal. The gradient is 0. Okay, so now again, after you calculate all the critical points, we have to do a second derivative test. Here, that means computing the Hessian. So we're going to check the Hessian. Remember that the Hessian is actually a matrix. So whereas previously we're checking the sign of the second derivative, we now have to check the definiteness of the Hessian matrix evaluated at the critical points. So if the Hessian is positive definite, then we have a local or global minimum. If the Hessian is negative definite, then we have a local or a global maximum, this case. If the Hessian is indefinite, then we have a saddle point. So this is kind of like a new case that we didn't have before. So if Hessian is indefinite, we have a saddle point. So that looks like this. So remember that indefinite, the concept of indefinite only exists when we have more than one variable, right? Because a single variable is either greater than or less than or 0, right? It cannot be both. So indefinite means positive in some direction, so opening up in some direction, and then opening down in other directions. Okay, the last case, if the Hessian is positive semi-definite or positive or negative semi-definite, this is actually the inconclusive case. And the function could be, so the critical point could be a local or global minimum, a local or global maximum, or a saddle point. So remember, indefinite is actually not the inconclusive case, right? In that case, we get saddle point. Semi-definite is actually, whether it's positive or negative semi-definite, that's the inconclusive case. Okay, so in general, the functions can be, so I guess maybe one pattern you see is that I always do local/global because these tests don't actually tell us whether we have like a global minimum, meaning that the function is the lowest here compared to everywhere else, or it's just the lowest here compared to the surrounding points, right? So in general, the derivative tests cannot tell us whether something is local or global. However, when the function is convex, then we can simply then every local optimum means minimum or maximum. So every local minimum would be also a global minimum. So this is only true for convex functions. Actually, even better, if a function is convex, then every critical point is a local minimum. Okay, and therefore every local minimum, and because local minimum means global minimum, then every critical point is actually a global minimum. So you don't even need the second derivative test for convex functions. Okay, as you can expect, it's the other way for concave functions. If the function is concave, then every critical point is a local maximum. And because every local maximum is also a global maximum, every critical point is a global maximum. So it doesn't actually go the other way around, right? So there are some other functions. So there are some other functions which are non-concave, for example, where every local maximum is also a global maximum. So for example, this function. So this function is actually not concave because there are some points, i.e. there exists, okay, I can't see that color, 1 second. There exists some points, say these 2 points, such that when I draw a line between them, the line is above the function. Right? So even though there are some other points where if I draw a line, the line is below the function, not every pair of points will give me something that is below, right? Some pair of points will give me a line that is above. So this function is not concave. So there are some non-concave functions where local maximum is actually a global maximum. So local maximum being global does not imply that the function is concave. But if the function is concave, then that implies that local maximum is global maximum. Okay, let's take a 10-minute break and then we're going to continue with some examples. Okay, let's look at some examples to look at some of the more difficult cases. So let's take a look at some actually variable functions of one variable. So let's look at f of x equals x to the power of 4. If you take the derivative twice to compute the second derivative, you would get 4 comes down. So, okay, maybe we should actually just write this out very quickly. Okay, so I need more room. Okay, so we have f of x equals x to the power of 4. So f prime of x. By the way, the function looks like this. It kind of looks like a x squared function. It doesn't go below 0. Sorry for my drawing again. It doesn't go below 0. So it looks kind of like x squared, right? Except it's more flat at the bottom in the middle here. And then it goes up faster as you go to the two sides. Right? So that's x to the 4th. So the first derivative is going to be 4x to the power of 3. Second derivative is 12x squared. So we can see that. So mathematically, f double prime of 0 is 0. But we know that at x equals 0, we have a local, in fact, a global minimum. So this is a case where when the second derivative or Hessian, so in this one variable case, we say second derivative is 0. The equivalent thing in multiple variables is really Hessian PSD, positive semi-definite. So actually it turns out that PSD is actually a very common abbreviation for positive semi-definite. So in the case where Hessian second derivative is 0, the inconclusive case, as we remember, right? The inconclusive case for multiple variables would be Hessian being PSD. So in this case, we actually have a local or a global minimum. But we can easily see that, we can easily see that if we simply define f of x to be case number 1, case number 2, is when f of x is negative x to the power of 4. Hopefully you can see that f double prime of x will be just the negative of before, and f double prime of 0 also equals to 0. Right, so here we have, again, Hessian PSD, or maybe negative semi-definite, right? So this is the inconclusive case. So basically inconclusive based on second derivative test. Well, in this case, hopefully we know that negative x to the power of 4 looks something more like this. So this point is actually a local maximum, right? Or a global maximum. Okay, so this example is just a very simple example showing that when we get to the inconclusive, when we get to the what happens when we're in an inconclusive case, and perhaps just give you some idea of why they may be inconclusive. At a higher level, the reason sometimes these tests don't work is that, let me go back here, the first and second derivative and kind of analogously, the gradient and the Hessian, they only capture the first and second order behavior of the function. In the example that we had, we have something x to the power of 4, right? So that means that the first and second order approximation of the function does not actually tell us enough for us to draw a definite conclusion about local maximum or minimum, right? So all the analysis using gradient and Hessian, they're just first order methods for understanding the change of the kind of the rate of change of the function and the rate of change. But when the function has zero rate of change and zero rate of change, you can't really say anything by looking at the first or second derivative tests. In this case, we will probably have to look at we have to take 4 derivatives before we can draw any conclusion. Okay, so that's kind of like a more higher level mathematical intuition. Okay, so next concept, it's called the Lipschitz continuity. So this is just a definition. So a function f of multiple variables as input, one variable as output is L Lipschitz if for all input vectors f of x1 minus f of x2, the absolute value is always less than or equal to some number L times the 2 norm of the difference between these two vectors x1 and x2. So this is the distance between the vectors. So the intuitive meaning of this is that an L Lipschitz function cannot grow too quickly. It cannot change too quickly, actually. So that means that if I start from x1 and I move to another point x2 that is some distance away, the resulting change in the function value cannot be more than L times this distance, right? So that's kind of how you literally read the math. So an everywhere differentiable function is actually L Lipschitz if and only if, that means equivalent to the gradient of the function being less than or equal to L everywhere. So in this scalar function example, I have just drawn this purple function, which is L Lipschitz. So L is just a fixed number. It can be anything. So in this case, I have decided that L is going to be this particular slope of the of this line here, right? And then the negative slope would be negative L slope would be that other slope. So basically, the purple function does not change faster than these two slopes. So therefore, this purple function is a L Lipschitz. Sometimes people will say Lipschitz continuous with a Lipschitz constant of L. So L is called the Lipschitz constant. Okay, I think that's probably enough about convexity and Lipschitz continuity. Let's just take a few moments to review a little bit. Okay, so take a look. Okay, obviously, yeah, so this is really true or false, so don't worry about these two. Right, so look at A to E, decide whether they're true or false. I'll give you about 2 to 3 minutes, I guess. Okay, let's take a look. So first, computing A inverse, where A is full rank but non-square. Okay, so it turns out that we cannot do this. Okay, because non-square matrices are not invertible. So we cannot compute the inverse. Okay, so that's a more basic, I guess, fact about matrices. Next, computing the square root of x transpose ax, where A is non-square, is that always valid? So it turns out that this is always a valid operation because we have already demonstrated that x transpose ax is always greater than or equal to 0, no matter what a and no matter what x. So the inside is just going to be some non-negative number, and we can definitely take the square root of a non-negative number. Okay, next, computing x transpose ax, where a is symmetric. Okay, so this is actually no, we cannot always do this. So we can do this if a is positive semi-definite. If a is positive semi-definite, then this result will always be non-negative, and therefore we can take the square root. But if a is, for example, negative definite or even indefinite, so basically anything except for positive semi-definite, then the result of the quadratic form might be negative, meaning that we cannot actually take the square root. Okay, so next one, computing the eigen decomposition of A, where A is non-square. Okay, turns out that we cannot do this. Eigen decomposition can only be applied to square matrices. And lastly, computing A divided by B, where A and B are positive definite. Okay, so kind of a trick question here, but the answer is no. So we cannot divide matrices. So the closest thing to dividing matrices would be multiplying by the matrix inverse. So sometimes, so maybe you can think of this A divided by B as AB inverse, right? But actually, strictly speaking, we cannot divide. And the reason is that we can write down A B inverse, but we can also write down B inverse A, right? So it's kind of unclear which side the B inverse might be on, the left side of A or the right side of A. And we know that for matrices, the results can be different depending on the order, like depending on which matrix comes first. So we cannot actually divide matrices. Okay, so hopefully that's clear. If not, again, I'd be happy to answer your questions on the courses forum. Okay, another review. Yeah, take a look. Okay, let's take a look at this question. So do each of the following characterize a convex function? Okay, so which of these choices characterizes a convex function? So actually I'm going to start with C here. So what C is saying is that the Hessian of f is positive semi-definite. So we talked about this is a property of convex functions, right? This is equivalent to f being convex. So for sure is yes for C. Okay, so now C is yes. It turns out that D and E are actually the same thing as is saying the same thing as f is positive semi-definite. So D, all eigenvalues of the Hessian of f are non-negative for every x. So this is saying that the Hessian is positive semi-definite everywhere. So this is actually the same as C. Okay, and E is also just another way of saying C as well. So let U lambda U transpose equal to the eigendecomposition of the Hessian. And then the diagonal entries of lambda, which is the matrix containing all the eigenvalues, are non-negative for every x. So again, that's simply just saying that the Hessian is positive semi-definite for every x. Okay, so these three, hopefully you were able to see. So this is more like a review of what it means for a matrix to be positive semi-definite. The main thing that we have to watch out for in this case is really this for all x, right? So whenever we take the Hessian of a function, in the scalar case, it would be the second derivative. The value actually depends on what x you plug in, right? So where are you taking the Hessian or the second derivative? So all of these are saying for all x, no matter what x you plug in, the Hessian is going to be positive semi-definite. So that kind of brings us to the top two choices, or the top two parts. So let's take a look at B. So B is saying that we're going to construct a quadratic form using the Hessian in the middle. And in the Hessian, we actually, so in the Hessian, the argument is actually y, and the choice is saying for all x and y, the quadratic form involving the Hessian is always non-negative. So B is actually yes, because that's actually just another way of saying the Hessian is positive semi-definite everywhere. Okay, so this is really important with the two different variables here. The x variables are only there to construct the quadratic form, whereas the y variable is kind of like the x that we had earlier, and that's saying that no matter where you evaluate the Hessian, so no matter where you evaluate the Hessian, you can always construct a quadratic form such that the entire quadratic form will always evaluate to something non-negative. And that brings us to A. So A is actually the only one that's a no. And the reason is that basically it doesn't really have, it's not really saying that the quadratic form or the Hessian is always positive semi-definite everywhere, right? It's only looking at a single value of x, which happens to match the argument of the quadratic form. So even though this might be true, like even if you have this quadratic form being non-negative for all x, there could be, if you plug in something else in here in the argument of the Hessian, you actually may get a negative value, right? So the for all x and y is pretty important. Okay. So with all of the math out of the way, we're finally ready to look at the first topic in machine learning, and we're going to be using all the math that we just did. So the first topic actually involving machine learning is linear regression. So we kind of introduced a picture of this a little earlier when we talked about how the child machine that we're trying to teach is what we called the model in machine learning. And the blank sheets, so kind of the blank sheets of the child machine is the model parameters. And the teacher, how do we teach the machine? We teach the machine using a loss function. right? So I think, so the model is basically the first line here. The model takes as input x, and it produces a prediction y hat. W and B are the parameters. Depending on what W and B the model has, the model will predict a different y hat. And how do we know how good the prediction is? Well, we assume that we have a lot of data points, x and y. So x and y are shown in as the blue scatter plot here. So in this one very common loss function is actually L equals to y minus y hat all squared. So basically this penalizes any deviation from the data points. So if your prediction y hat is far away from your data point, then you get penalized according to this formula. So deviation below the ground truth or the data, and as well as deviation above the ground truth or the data, they are penalized equally. Okay, so we kind of so we saw this earlier, and earlier I also mentioned that we would like to find the parameter values W and B that minimizes the loss, and mathematically this is written as W star B star. So the star, I will usually use star to denote optimum or the optimal value, equals to argument minimum or just arg min over W and B of L, the loss function. So now we're actually going to take a look at how this can be done. But let's set up the problem a little bit more rigorously. So let's look at what we're given. So we're given a data set of input-output pairs, also called observations. So these are going to be denoted as xi, yi. So each xi, yi would be a data point, and then the data point indices go from I equals to 1 to capital N. So given the set of data points, we would like to construct a model to predict the output y, also called the labels, from the input x, called the data. So I'll usually just use input and output just to keep things simple, but you may see data or labels elsewhere. So now we can choose a linear model, which is the simplest kind of model, y hat equals wx plus b, where y hat is the predicted output or prediction. Okay, so in general, actually, the model doesn't necessarily need to be linear. The model could actually be any function of x, right? So we just want to be able to plug in x, and some function f will give us the prediction y hat. And of course, the prediction depends on the weights w and b. Coming back to this particular case, we have chosen the function f to be a linear function, wx plus b. So it's really important to note that x is going to be given in this case. So w and b are actually the unknowns, and we would like to determine the unknowns. So how do we determine them? Well, we define the loss function L of w and b. So this emphasizes that w and b are the unknowns, and it equals to the loss function that we saw earlier, except that we're going to add up every data point. We're going to add up the loss function contributed to by every data point. This particular loss function is called the square loss. Okay, so basically what's really happening is that, so let's say that this is data point I. We're going to take the data point I has a certain y value. So you probably can't see that. Okay, so this data point y, so this data point I corresponds to what we want to obtain if we plug in x, the y value that we want to obtain. So that would be yi over here. The model, which is the red line, is predicting some y hat, and we take the y hat, so yi hat, and then subtract yi, so this distance, and then square that, and that will be the loss. That will be the loss contributed by this particular data point. We do that for all of the data points. That's why we have a summation over all the data point indices. Okay, so now, given a w and b, we're just going to have some corresponding straight line, right? Maybe a straight line could be like this for certain choices of W and B. The straight line could be something like that for another choice of W and B. We would like to find W and B such that all of these losses are minimized. So the sum of the square distance, so the sum of the square vertical distance between the line and all the data points are minimized. Okay, so let's do a little bit of math here. So again, I'm just going to write down, okay, actually, let's do this a bit more slowly as well. This will be pretty important. Okay, so we would like to minimize over W and B of the loss function whose arguments are W and B, right? And this, so in the future, I'll probably not write the entire word minimize. I'll just write min. Okay. So summation from I equals 1 to n of yi minus y hat I squared. Okay, strictly speaking, we actually should not be writing the entire word minimize. So kind of a technicality. You can ask me that later, but yeah, this should be min over WB. So in general, okay, so let me just continue writing. So in general, the y hat is actually given by the model that we choose. So some function x, which is a function of x and w and b. So our model f takes as input xi, so the ith input, the ith theta, and predicts y hat. And then we subtract what we want, the desired output yi, from this f, and then we square that. In our particular case, we have chosen a linear model. So it's yi minus wxi plus b. Okay, all of that squared. So the problem is, how can we choose w and b in this expression such that this summation is minimized? So the summation actually involves n terms, right? So we're adding a lot of things together. This entire expression has w and b appear in many of the terms. We would like to pick the w and b that makes this quantity the smallest. So that's what we're doing. So how do we do this? Okay, so let's see. Maybe we can. Yeah, actually, let's talk a little bit more generally. So what we wrote on the previous slide is basically assuming that the input is a scalar and the output is a scalar. So this is a very simplified case. In many cases, the input could have multiple dimensions. So for example, if we had a pixel if we have an image as input, then x could be the set of all the pixels, for example. So that means that our input has many variables inside, many components inside. In that case, we would need a slightly different model. In that case, the simplest model is actually y hat equals summation over j equals 1 to n of wj xj plus b. Right, so if we come back here, so with vector inputs, in general, we have a vector input. That just means that the input has many components. we can change our model slightly, right? The model would just be y hat equals f of x, now a vector. Let me not do this. Yeah, sorry, just 1 second. Let me just write everything out. So it's actually, our model will be a function of all of the components of x, and then the outcome depends on our weights. So how do we generalize? So above here we actually had, so the simple model we had here was y hat equals wx plus b. So what is the simplest way to generalize this? Well, the simplest way of generalizing this is really to have a different w for every I, for every component of x. So for x1, we multiply by w1, and then we have w2, x2 plus until wn xn. Should be wn xn, and then plus b at the end. So this is the most straightforward generalization of our previous scalar model. But we can actually write this more compactly using vector notation. So what we really want to write is x vector f of y hat equals so y hat equals x vector, and then w and b, and that actually equals to w transpose. In this case, I guess I need to write w needs to be a vector as well, right? So w vector transpose x vector. So this is just the inner product, and that expands out to this sum here, plus b. Okay. So it's kind of seems a little clumsy. Actually, it will be a slightly more convenient if we define the x vector to be equal to x1 all the way up to xn, and then we actually add a constant 1 inside this definition of the input vector. This will actually simplify things a little bit. Okay, and then we have to define w equals w1 all the way up to wn, and then we're going to include the b. So if we define it this way, then we can actually write y hat, our model, in an even more compact form, which is simply w transpose x. That's all. Right? This is the simplest version. You can kind of see that the xi's are multiplying by the wi's, they all add together, and at the end, the 1 multiplies by the b, so that's how we get the plus b here. Okay, so this is the most compact form. So given this form, we can now write down our loss function. The loss function is now just a function of w, because the w includes the b in here. So we're still going to add up over all the data points, I equals 1 to n, and then it's always going to be yi minus yi. So yi, this is the desired output, this is from the data, and then minus yi hat squared, and then this equals to summation from I equal 1 to n of yi minus w transpose x, all of that squared. So for now, yi is still a scalar, but w and x are vectors. Okay, so that's what we have here on this slide, right? So the most straightforward way to extend our model to take multiple components as input is going to be just adding up all, like taking a linear combination of x using all the weight components wj. Okay, so then the first step, we can write it like this. So this kind of looks like the previous model over here, right? Or even earlier over here. But it turns out that since we're using vector notation anyway, we may as well define w to be, we may as well define w to include b as well, and then we can define x to include 1 as well, and then we can simplify our model. Okay, so that's the simplified model, and then the loss function becomes sum from I equal 1 to n of yi minus w transpose xi. All of that squared. Okay, so the next step is actually trying to minimize this loss function. Okay, to do that, there are two ways, a hard way and an easy way. We're going to start with the hard way. So we're probably going to just introduce some of the ideas today, and then actually work it out in detail next time. So the idea is that we're going to take the gradient of L and set it to 0. This is kind of analogous to in first-year calculus, you took the derivative of a function and then set the derivative to 0. So we would like to find what w will make the gradient of L 0. To do that, we're going to be taking, just looking at the jth partial derivative of L. So remember that the gradient is actually the kind of all of the partial derivatives put together in a vector, right? So we're just going to look at what the jth partial derivative looks like. Okay, so our loss function is this summation of a bunch of squared terms. So when we do the partial derivative, the 2 comes down, the inside stays the same, and then we have to use the chain rule and take the partial derivative of the inside with respect to wj. So for this one, we're going to go through it quickly today, and then we're going to repeat it again tomorrow, next time in more detail. Right. So here, the only term of w transpose xi that depends on wj is going to be the jth term in the inner product. So that's why in the jth term is basically negative wj xij, the jth element of xi. So then we have negative xij out here. Then we do some simplification here. And then we move everything involving w to one side. So that's basically this term. The 2 cancels out. And then the yi xij goes over here. And then finally, we expand out this inner product. So now we're going to have another summation over k from k equals 1 to little n of wk xik. So this part is basically this inner product. Everything else stays the same. Okay, so next is going to be a series of simplifications. So first we switch the order of a summation and pull the wk out. So now this is kind of as far as we can get using the summation notation. So next we're going to do a series of observations. The key observation here is really that whenever we have a summation of two things, a summation of a product where the product basically is indexed by the index of the summation. So this is actually, this looks like an inner product. So next time we're going to be figuring out exactly what inner products are involved. So hint, there's one inner product here, one inner product for each row of the matrix, and then multiply by y. Over here, we have an inner product between wk and another inner product. So this inner product is going to be written down as a matrix multiplication, and then each row of the result of the matrix multiplication will actually be multiplying by w. Right? So it's all a little bit complicated, but we're going to work this out next time. So then we kind of make some interesting observations. For example, these matrices are pretty similar, and that gives us this equation, which is called the normal equations. And in some cases, for example, when x is full rank, you can actually solve for w here by taking the inverse of w of x transpose x. So this will be the hard way that we're going to work out in detail next time. The easy way is actually to make everything vectorized from the very beginning. And that's basically realizing that our loss function can actually be written as a 2 norm. We can then expand out the 2 norm and then get a kind of a, I mean, still a bit ugly expression, but much nicer than before. We can then take the gradient of this expression directly using matrix derivatives. So we're going to talk about matrix derivatives next time, and then we can actually obtain the best W that minimizes the L function actually reasonably quickly. So yeah, again, more matrix derivatives that we're going to be covering. And finally, after taking the matrix derivatives, setting the gradient to 0, we actually get the same optimal W. So all of this is coming up next time. So I think we're pretty good for today. So I'll see you guys next time.